Good morning, everybody. I am Elio Matteo Curcio and I'm very glad to show you our work, which title is Shape Memory Alloy Reinforced Composites. Functional structural response induced by thermal activation. This work has been done in collaboration with Stellantis company. The project is called AREA, that means Active, Responsive, Intelligent Aerodynamics. The project aims to develop aerodynamic deformable surfaces that adapts their shape to the car's operating conditions. Starting from the first fluid dynamic analysis, have been identified some aerodynamic devices that will suit for the purpose, changing the aerodynamic parameters. Three main tasks have been identified. The first one is to develop active aerodynamic devices. The second one is to build up a design tool to evaluate the effect of SMA actuators on aerodynamic devices, and finally to design and develop prototype demonstrators. Our team's purpose is to design the metal poly interface, analyzing the overcoming some technical issues ongoing during the design. In literature it is already possible to find examples of prototypes working in aeronautical fields and others, which use SMA actuators to provide shape morphing. The common working principle is to cast SMA material inside the device, under wires or sheets shape, away from the neutral axis of a component. The contraction produced by SMA generates a concentrated moment that allows the bending of the device. A temperature material sensitive allows to realize a device that adapts their shapes to the surrounding environment in a smart way. The presentation will be articulated according to the following points. I will introduce the SMA and their characteristics. We will see how it's possible to simulate SMA material and how it's possible to characterize them. And at the end, the results that can be achieved in this ambitious project. SMA means shape memory alloy, which are a class of material composed by nickel and titanium in around equiatomic percentages. They have three fundamental properties: the pseudoelastic effect, the one-way and the two-way shape memory effect. The material has two crystal structures: austenite at high temperatures and martensite at low temperatures. The martensite has a distorted atomic structure, called twinned martensite, that can be reorganized into an aligned structure, called the twinned martensite, resulting in an overall deformation. By going to the twinned material, you can accumulate a residual deformation, like a spring that accumulates potential energy. The shape memory effect is provided by the phase change between the two crystal structures. Temperature plays a key role for the SMA. Phase change is achieved through heating from martensite to austenite, or cooling from austenite to martensite. From the variation of the martensitic fraction that turns to austenite, it's possible to derive the start and finish temperature transformation of the single phase. Stress also affects the phases. In fact, a material that is already in high temperatures, like austenite, can be transformed into martensite by applying a mechanical stress. The property that is exploited for the realization of adaptive surfaces is the shape memory effect. It consists in the recovery of a residual pre-deformation downstream of a thermo-mechanical training. The material looks like the twinned martensite, is heated turning into austenite and recovering the deformation. Austenite is stiffer than the martensite, and thanks to this property is possible to provide device deformation. Due to the amount of involved parameters, the device design is very complex, so it becomes necessary to understand if a thermomechanical variation occurs during repetitive activation cycles and identify the correct operating condition to prevent material degradation. Some investigations have been carried out by other authors. To simulate the behavior of SMA, a numerical model has been developed based on Brinson work. The model estimates stress and strain of a monodimensional element as wire under mechanical and thermal load. The model takes into account the mechanical properties of the phases and the variation of the martensite fraction induced by stress or a thermal load. The model was expanded to simulate the behavior of the design prototype. A thermal model has been introduced to simulate the joule heating and takes into account parameter variations such as electrical resistance and thermal capacity as a function of the martensitic fractions of the material. The model was implemented in Simulink, realizing a design tool fully customizable. The model can take in input mechanical parameters such as stress and strain, and energy such as temperature or electric voltage. These parameters can be calculated separately and allow to communicate complex mechanical model with SMA components. For example, it is possible to simulate the addition of a SMA wire embedded into a resin block to evaluate the mechanical addition at the interface, by modeling the two systems separately. The preliminary adhesion tests have been carried out. The components are very complex and present particular problems of metal-polymer integration that compromise the structural integrity of the component. These are only few tests and require more investigations to assess the feasibility of the SMA-based composites. The present model needs tuning parameters that can take place through experimental tests. Through a tensile test, mechanical parameters such as Young modulus, the tuning stress and transformation strain can be obtained. Stress-free transformation temperatures can be obtained by DSC tests. Investigating the functional properties of SMA, a property degradation can be observed during the activation cycles. This observation results in a deeper analysis to understand stable operating conditions. To get the main parameters such as stress, strain, and transformation temperatures, a frame has been built for our purpose. By acquiring the signal through load cell, linear variable displacement transducer, and infrared camera, the shape memory properties were evaluated. The carried out tests have shown a significant variation of the hysteresis cycle as a function of the activation cycle at different load conditions. For this reason, it becomes fundamental the identification of the operating parameters for the stable operating condition. The deformation temperature plots show the phase transformation temperatures variation. The overall trend depicts an increase in temperatures together with the load. Thanks to the transformation temperatures, the phase diagram is provided. Output parameters from the tests are given to the model in order to better simulate the real behavior. Through this tool is possible a correct design of the component. The output plots from the model show a fitted temperature, but it's clear that a better tuning for a deformation temperature cycle is necessary. However, the tool is useful for a correct design of the first concept. Here the videos show a bending actuator inside a wind tunnel. For this device there are 4 SMA wires with a diameter of 0.3 mm each. As you can see, the components are correctly activated. In conclusion, an electro-thermo-mechanical model has been presented that allows to design of shape memory alloy based in an innovative device. The first prototypes works under different operating conditions, and an effective procedure has been identified for the characterization of the material. The model needs some improvements such as load history and functional degradation that will be implemented in later version. In addition, a model will be inserted to simulate the mechanical and fluid dynamic interaction. The final components will be installed and tested on the real car. Thanks for your time.